All right. Hey everyone. This is our Saturday class, and I just want to take it easy in this class. I don't want to do too much because I really value our time together when we're working together. So in this video, I want to do something, and it's optional to watch. You're not going to learn anything that you absolutely need in this class, but you might learn something interesting that'll be useful when we're writing proofs. And so what I want to do is I want to prove that there exists a number in R such that x squared equals 2. Okay. And remember that this is not true in the rational numbers. Right? So this isn't true for the rational numbers. We proved that remember I made a video about that. There's no square root of 2 in the rational numbers. Right? And so if we think about those axioms that we have, remember we had those ordered field axioms. And then we had the completeness axiom. And the ordered field, well, Q was an ordered field, R was an ordered field. But if we threw in the completeness axiom, the only thing satisfying all of these was a real number system. Okay. And so I know I'm not going to be able to prove that the rational numbers has a square root of 2. And so I must use the completeness axiom at some point. And we'll see where I do that. Okay. So let's do it. So before I dive into the proof, I will mention there are much easier ways to prove that there is a square root of 2 once we have more machinery. And so later in this course, we will prove two things. We'll prove the intermediate value theorem, which says that if we have a function that is continuous. In fact, let me just say what the domain is. Let's say we have a function from a, b to real numbers. This means the domain is some interval a to b, and the output is the real numbers. And I'm going to draw a picture of what that might look like. So here's our interval from a to b, and we have some function. And I don't know what the function looks like. And suppose that we know that f is continuous. Okay, so we haven't defined continuous in this course, so that's going to be to do, and not in this video. Again, this is like a different way to prove this. But we're going to, in class, talk about what continuous functions are. And we're going to say that if f of a and f of b have different signs, meaning one of them is positive, one of them is negative, then there must exist some point in the middle such that f of c equals 0. And this is the intermediate value theorem that maybe you remember from calculus that says, let me kind of erase this function. If all we know about the function is that maybe f of a is positive and f of b is negative, then somewhere, because of continuity, I don't know what the function does, but at some point it has to cross that x-axis. And so there has to be some point c where our function is exactly equal to 0. Okay? And so later in class, again, later we're gonna define what continuous means. We're gonna state the intermediate value theorem. We're gonna prove the intermediate value theorem, and then we're gonna do as an application. It'll just be a wee example. We will show that f of x equals x squared. It's a function from, I guess, all the real numbers to all the real numbers, is continuous. You're probably not very surprised that this parabola is a continuous function. It's very reasonable. And what you are, in fact, let me apply it to x squared minus 2. It's continuous. And what we're going to do is we're going to look at the graph of this. And we're going to say, I don't know what this graph looks like, but I know that f of 0 is -2. And f of, I don't know, 5 is 23. And so whatever this parabola is, because at 5 I got a positive number, and because at 0 I got a negative number, I know that this graph has to cross the x-axis somewhere. So that has to cross somewhere at c. So by the intermediate value theorem, I know there exists a number c such that f of c is exactly 0. Okay? In fact, I know that c has to be between 0 and 5. Okay? And what do we know? What does this equation mean? If f of c is 0, that means that c squared minus 2 equals 0. And that means that c squared is 2. And so what did we find? We showed that there was a c in between 0 and 5, so it must be positive. And c squares exactly to give us 2. So if you want to show that the real numbers has a square root of 2, this is great. All you've got to do is define continuity and prove the intermediate value theorem, and then prove that quadratic polynomials are continuous. And then by the work that's on this screen, that's it. That's going to be a full proof that the square root of 2 exists. Now, we haven't done any of that, and it's going to take us another 2 months to do all that. And so today I want to show how we can find the square root of 2 in the real numbers just by using the axioms. And it may or may not be to your taste, but I hope it's at least kind of interesting. And you may get to see me think on my feet and make a mistake or two. And so I hope that you are okay with that, because it may happen. All right, so here is our existence of square root of 2 from the axioms. All right, so what did I do? I said I would show you, as I want to show that there exists a number x that's positive in the real numbers. That's a really pathetic r. I'm gonna draw a better one. So that x squared is exactly 2. Okay. And now I'm going to do a proof. And it's been a long day, so I'm going to switch to a more pleasant color. I'm going to switch to whatever color this is. So proof. I am going to define a set. I'm going to let S be a set of all numbers in R. Now, I don't know that there's a real number that squares exactly to 2. Right? We haven't proved that yet. And, you know, it's not obvious, right? There's no number that squares to give me -5. So, like, maybe there's no number that squares to give me exactly 2. So what I'm going to do is I'm just going to look at all things such that if they're positive, and if when I square them, I'm going to get something less than or equal to 2. Okay. So I can at least define that. I can say, well, look at the real numbers, look at the ones that are positive, and square them and see if it's bigger or less than 2, right? And so I can just check, right? Like I can just check 1. Well, 1 squared is less than 2. Okay, so I guess that means 1 is in S. And 3 squared is not less than 2. Oh, so I guess 3 is not in S, right? So some numbers are in S, some numbers aren't in S. And in fact, if you have kind of a picture of a number line in your head, what is this? Come on, line. There it goes. if you think about what this is, I mean, really what S is it's all numbers between 0 and the square root of 2, right? We know that because we know that there is a square root of 2. And if we take a positive number and we square it and we get less than 2, it's going to be in this range. So really, we kind of know what S is, but at the very least, we can check whether like a number like 1 or 3 is an S. Okay. So I'm going to get rid of this work. I'm going to leave the number line for a second, but I'm going to get rid of that in a second too. What I'm going to do is I am going to let X be the supremum of S. And according to this picture, the supremum of S really looks like it should be the square root of 2. Right? And so in our goal, I want to find a number X that squares to give me exactly 2. And here's how I'm going to construct it. I've got a set. I'm going to let X be the supremum of that set. And then I'm going to show, we will show that X squared is exactly equal to 2. And you're going to see it's pretty hard to do that, okay? So get a cup of coffee or something, right? So I'm going to get rid of this picture. Actually, I'll leave that picture for a second. Okay. So, in fact, I'll just remove this label here and just kind of label this as an X. Whatever the supremum of that set is, I'm going to call it X. Now, why does this set have a supremum? And why is that supremum a real number? Well, we're going to have to show that this set is non-empty and bounded above. Right? So first of all, we already checked that 1 is an S. So S is non-empty. And I claim that S is bounded above by let's say it's bounded above by 10, right? Right. I'm kind of thinking this is like the square root of 2. It's probably like 1.4. I'm thinking that this set is going to be bounded above. And now once I know that my set is bounded above, then I'm in good shape. Then I can take the least upper bound, and I'm going to know that X exists. And we still have the hard work of showing its square is equal to 2. Okay. So why is this set going to be bounded above by 10? Okay. So I claim that S is bounded above by 10. Indeed. Let Y be an element of S. Okay. Then what do I know? Well, I know that Y is a positive number, and I know it squares to less than 2. Right? So I know that Y squared is going to be less than 2. Now, what would happen if Y were bigger than 10? If Y were bigger than 10, then what would Y squared be? Well, I think Y squared would be bigger than 100. So this would contradict that Y squared is less than or equal to 2. Okay. So therefore, Y must be less than or equal to 10. So this means that 10 is an upper bound for S. And so we've shown that the set S is bounded above. Right? We know it's bounded above by 10. We just picked that kind of because we needed some number bigger than that. I could have picked 8. I could have picked 3. I could even pick 2. Right? But I know it's bounded above. And so I have, I'm going to take that number to be the supremum. And actually, I am going to change something now, right? I'm going to change one thing, and I'm going to tell you why I'm going to change it. If you notice when I define my set S, I use the letter X. And X is just a placeholder. It means I'm looking for those things that are positive and those things squared to give me less than or equal to 2. Because I did that, I'm going to, just in my problem, I'm going to say I'm looking for a number. I'm going to call it B. And I want to have B be the number that's the square root of 2. I just don't want the X, I don't want there to be any confusion as to the difference between this number B that's ultimately going to be our square root of 2 and kind of the placeholder in that set notation. Okay. And so now I will show that B squared is equal to 2. So now I want to point out that I've just used the completeness axiom. You might not have noticed it, but right here, when I took the supremum of something, I'm taking the least upper bound of a set. Right? And so we use the completeness axiom here. So, i.e. B is the least upper bound for S. And I know the only way I can say that a set that's bounded above has a least upper bound is appealing to the completeness axiom. So, you know, that's just what we need in this case. And so now I will prove that B squared is exactly equal to 2. Right? And I will do this by contradiction. And what I will do is I will do kind of two cases. I actually might get tired and just do one case. And if that happens, then if you do case 2, I will give you extra credit. And when you talk about it, I can give you extra tokens if you want, or I can just add some points back to one of your quizzes if you want to write this out. Okay. In fact, I'll just say that's what I'm going to do, because I know these cases are going to be long. And so case 1, I'm going to argue by contradiction. I'm going to say, well, what would happen if B squared was less than 2, right? And so I'm gonna write a proof. We're gonna say, man, what would happen if B squared was less than 2? Boom, contradiction. Right? So that means that can't happen. Okay. Now what about case 2? Well, case 2, that'll be your proof that B squared is greater than 2. And we're gonna go boom, 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 contradiction. Okay. And now if we think about what happened, well, I was going to show that B squared, well, I mean, B is a number. B is a real number. So B squared is a number. And it can't be less than 2, and it can't be greater than 2. Oh my gosh. B squared must equal 2. And then we're done. So this number squared is exactly equal to 2. So I'm going to take all of this, I'm going to shrink it down to, I don't know, something very, very tiny, just so it's in the notes. And I'm going to move back to our main case. And I'm going to get rid of this contradiction, because I know what's coming, and I know it's going to be a lot longer than we think. Right? So I am going to show that B squared cannot be less than 2. I'm going to get a contradiction if we assume that B squared is less than 2. Okay. And so here is how that's going to go. Okay. So let's assume, and let's switch colors again, because why not? So let's suppose that B squared is actually less than 2. Okay. Well, what do I know? Well, let's actually draw our set S in one more time. Here's 0. Here's B. So here's our number line. So here's B, which again we know is going to be the square root of 2. And here's 2. And here is our set S. Okay. And what are we supposing? Well, we are supposing that B squared is smaller than 2. Okay. And so wherever B squared is, it's somewhere to the left of 2. It might be really, really, really close to 2, but it's going to be somewhere smaller than 2. Okay. And so let's give that a name. Let's see how far apart those two elements are. And so let's call this distance here, let's call that y. And so let y equal 2 minus b squared. Okay. That's the distance between 2 and whatever b squared is. We know that y is a positive number, right? Because 2 is bigger, strictly bigger than b squared. Okay. All right. So here's my idea. Here's what I'm thinking. I'm thinking, this is my thought bubble. Right? I'm thinking, since on this number line, here is b squared, and here is 2, I'm thinking that I could probably take b, and I could add a tiny, tiny, tiny number. Maybe I'll call it t for tiny. And if I square that, it would still be to the left of 2. That kind of gels with my intuition, right? If b squared is to the left of 2, if I add the tiniest, tiniest, tiniest little thing, it should still be smaller than 2. Right? And now is a good place, I would say pause the video, to go back and review and think about how this might help us. I'm deciding not. I'm gonna say that in a minute, but I'll let you think about that. Okay. And so I'm thinking that I could add a tiny, tiny bit. And so let's kind of work that out. Let's see what I need, right? So so that's my idea. So my idea is that I could somehow find a number t that works. And so what would that mean? If I wanted b plus some tiny number squared, and I wanted that to be smaller than b, what would I need? Sorry, smaller than 2. Well, that's b squared plus 2bt plus t squared. Okay, and I want that to be smaller than 2. Okay. All right, so let's put 2 minus b, 2 minus b squared. And then we have 2bt plus t squared. So I just rearranged some stuff. And oh my gosh, this thing here, 2 minus b squared, was y. And so this is going to be true as long as I can make 2bt plus t squared smaller than y. Interesting. Well, what am I going to do with t? Well, I could try and solve for t. That's going to be a mess and a half because t is, this is like a quadratic, so I'd have to use like the quadratic formula. I really don't want to do that. but I just want to show that there's some number t that works, right? And so I just want to find one t that works. And I'm imagining t is really, 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 really small, right? So let's assume that like t is like less than 0.1, right? It can be as small as I want. As long as I can get a t that works, I'm going to be happy. And so let's agree that we want t to be really small. And so then 2b plus 2bt plus t squared is definitely smaller than 2bt plus t, right? Because if I take a number smaller than 0.1, then I square it, it's going to get even smaller. It only needs to be smaller than 1, actually, for this to be true, right? But I'm just going to take a really small number. And, okay, so if I take, so this is true, right? And so if I want to get this whole thing, if I want to get this expression smaller than t, I can just make, sorry, smaller than y, I can just make that smaller than y. Okay? And so that, let's write that expression. That's t times 2b plus 1. And so if I want, let me just kind of summarize what my goal is, because I'm kind of running out of room here. If I can make t times 2b plus 1 less than y, then 2bt plus t squared will definitely be less than y. Right? Because it's, I mean, we just follow these inequalities. And so how can I achieve that? Well, I can just take t to be smaller than y over 2b plus 1. Okay. Right. So I can take t to be any number. I want t to be positive. And so I can take t to be any number smaller than that. Thus ends our thought bubble, right? I knew this was coming. This is why I told you we were in for a wild ride, right? So I'm just gonna delete that because we've got a lot more room to go, right? And so now let's take our thought bubble and let's see if we can translate this into something that makes a little bit more sense. It's maybe a little bit more readable. Because if you look at what I've written, it's kind of it's chaotic. Right? It made sense when I hope it made sense when I was kind of walking through it, but now we need to write it for a reader. Okay? And so I will now define t as any number between 0 and, what did I say? Y over 2b plus 1. So define t as any number between 0 and y over 2b plus 1. I could be explicit if you want. If you really want an explicit number, I could just let t be 1/2 of this number. Okay, I could divide it by 2. Right? I'm not going to do that because it's already pretty technical as it is. So all I'm going to use is that there's some number, that t is some number in there, but I could make it explicit, right? And so I've got definitely a number t, and now I claim that b plus t, if I square it, it's going to be less than or equal to 2. Right? And we're going to see, I'm going to prove that. I'm going to prove that claim. And then notice this means, and this is where, if you pause the video, maybe you saw this earlier, notice that this means that b plus t is an element of S. Wait, what the heck was S? Let's go back. Let's go back and see. S was a set of all real numbers, positive real numbers, that squared gave us something less than or equal to 2. b plus t, if my claim is true, then because it squares and gives me something smaller than 2, I mean, b was positive, t is positive, so b plus t is positive. That's going to mean that b plus t is an S. Right? Right? But this is a big, big, big problem, right? But b plus t is strictly greater than b. And what was b supposed to be? B was the least upper bound of S. So B was supposed to be bigger than or equal to every element of S. And we just found one that was bigger. We added a tiny, tiny, tiny bit to B, and we got something that was still in the set S. So that's a big contradiction. That contradicts that B is an upper bound for our set. Okay, and so let's try and complete this claim. Okay. So how do I finish that claim? Well, let's move this out of the way. In fact, I may need to add something about t. We'll see if we need that. Okay. So let's switch back to a different color. So proof of claim. So I need to compute b plus t squared. I need to show it's smaller than 2. And we already kind of did that. That's going to be b squared plus 2bt plus t squared. Okay. And, well, let's see what we can do. Well, remember earlier when we kind of wanted to use that fact that if t was a really tiny number, we wanted that t squared was smaller than t. I want to do that here. Right? But of course, t squared is only smaller than t if t is smaller than 1. Right? And I think in the thought bubble we said that t was smaller than 0.1 or something like that. So what I'm going to do is I'm going to go back and I'm going to modify this proof and just change the way that we construct a number t. Okay. So I'm going to choose any number t such that t is less than 1 and t is in that range. And this is a good place to actually pause and think about this. Right? And so remember earlier when I said, oh, just take half of this number on the right? Well, if you do that, and that number wasn't smaller than 1, then just keep dividing by 2 until you get to something smaller than 1. Or just, I mean, you could literally just let it equal 1/2 in that case, right? So there is always going to be a number that's in this range and definitely smaller than 1, right? Because if you think about what that range is, from 0 to y over 2b plus 1, right? I mean, we pick a number in here, and if it happens that that number was to the right of 1, well, we'll just pick a smaller one. And if it happens that 1 was like out here, well, then any number we pick in this range is going to be smaller than 1. Right? So that's something where I'm actually, I do want you to pause the video and kind of think that through. And send me an email. Send me a voice memo or something if you have a question about that, or we can schedule time to talk in office hours. But I do want to add this condition that t is less than 1. So, good. And so here, this inequality used that t was less than 1, so t squared is less than t. I guess I can make this a strict inequality. That's cool. Now I'm going to look at that. I'm going to say, okay, well, that is 2, let's see, this is now equal to b squared plus t times 2b plus 1. Okay, I just rewrote that and factored it. And now what do I know about t? Well, I know t is smaller than y over 2b plus 1. So we've got all positive numbers here. So this is going to be smaller than y over 2b plus 1 times 2b plus 1. Cancel, so that's going to be b squared plus y. And now what do I know about b squared plus y? Well, how did I define y? Y was the difference between 2 and b squared. So b squared plus y is going to be equal to 2. And so this is going to be equal to 2. And so was that my claim? Let's see, I wrote the word claim. I claimed that b plus t all squared was going to be less than or equal to 2. And I proved that b plus t squared, well, I actually showed it was strictly less than 2. Right? So I did it. And so this is so we have a contradiction. I guess I didn't write that. Let me put that here. This is a contradiction. And what we contradicted was that b was the least upper bound of our set. Now we still have case 2 of the proof to work, and as predicted, I am feeling pretty tired. And I think that if you're interested in this proof, if this speaks to you, if you think this is really cool, then try to write case 2 on your own. Try to find a contradiction to what happens if b squared is strictly greater than 2. And think about what would change. And think about what you would need to do. And I think there's going to be, I think that could be kind of fun. I think that would be kind of rewarding. And you're going to have to use maybe a different property of least upper bound. Right? So if you think about what we did in the first part, all we used was that b was an upper bound. And we found a number in the set bigger than it, which violated that. And in this other part up here, I think we are going to, the proof might be a little bit different. And so I'm going to leave that one for you. I know this video is already kind of long. And I'm going to wish you a happy Saturday or whenever you're watching this, and see you in class